section in our topic. Um, 4.4 is normal forces. Normal forces have to do with forces that are perpendicular or against an object that's sitting against it. Okay, so take a book on a table like this. This is a simple table, and a book is there. And that book, we know it has a downward force, okay, of Fg, but it also has this other force that's moving up. Now, if you think of it as sort of like little springs in on the atomic level of being compressed when the book is on the table, and that's what happens to support this upward force, which we use as F with a little perpendicular sign. So this F perpendicular is the normal force. It's also called the perpendicular force. And it's also called the support force. Okay, I usually use normal force. Okay, so it's in contact with something that's solid, usually, unless it's actually on the surface of water with surface tension. The surfaces are pushing on each other, they support one another, and the force is perpendicular to the plane of the surface. Okay? So, perpendicular to the surface plane. And the free body diagram for the book, I drew the forces on it, but for the free body diagram you make a dot for the object. The Fg is the force of Earth on the book, and F perpendicular is the force of the table on the book. Okay? So, for something that's leaning on a wall, like that, well, you'd have the Fg down, okay, and you would have F perpendicular would be like that, but you must also have some sort of balance to balance it out of friction that's holding that up as well. Let's take a look at a block sitting on a ramp at some angle theta of the ramp. And our block sit here. Well, in this case, the Fg would be down towards the center of the Earth, and the F perpendicular would be up like that. Okay? Now, this F perpendicular force, let's see if we can figure out what the formula is based on our Fg and the angle of the ramp. Well, just like we did when we looked at the value for g in a plane and we got g sine theta, we could do the same thing with our Fg. Okay? Just extend Fg down and make it a little easier like that. And then here's a 90-degree triangle right there. If that's 90 and this over here is 90, right? Then we have a 90-degree angle in the large one and a theta. Over here in the blue one, we know we have the 90 degrees. But also, if I look at this triangle, which is a combination of FG and the blue, it has a 90 degree angle. And so we have theta, which is over here, 90, and then we have this here. Now that must be, because it all adds up to 180, this must be the angle 90 minus theta. Okay? And if that's 90 minus theta right here, for this triangle, right? So in that green triangle, you have 90 theta and 90 minus theta. Well, that's also an angle in the blue triangle. So we got 90. This one is 90 minus theta. So this angle right there is also theta. Okay? And if that's the case, let's pull out that triangle, make it a little bit bigger over here. We got FG down, right? We got the plane, and we got coming up, and that's 90, and that's theta. So if we would like to know the component of the weight force in the direction of the plane, right here, we could get that. It happens to be, if we take sine of the angle theta, sine theta equals the opposite over the hypotenuse. Sine theta equals that new force, which we're going to call F parallel, because it's parallel to the plane, just like we had G parallel, over FG. So F parallel is simply FG sine theta, which makes sense. It's the same way we go about getting G sine theta, right? Now this force right here, that force in a similar method would be FG cos theta. Well, the opposite to that force is F perpendicular, this force right here. And so F perpendicular is FG cosine theta, like that, okay? So to get the normal force in the plane, it's equal and opposite to the force down, and just leaving off negatives for now, just FG cosine theta. So we have two equations, the parallel force, FG sine theta, and the perpendicular force, FG cosine theta. Okay, here's an example. A 50 kilogram object is sitting on a 25 degree ramp. Compute the weight of the object, the normal force the surface is providing, and the total force. The total force is also the parallel force, so I'm going to show you that. Excuse me. 25 degrees. We have an object. On that object, we have FG down. We have an F perpendicular. Now, if you took F perpendicular and brought it down, you could see that those two add together, head to tail, to give you this force, which is called the total force. And I dot it because what the total force really is just the component of the gravitational force in the plane, isn't it? It's the component of the gravitational force in the plane. So it's not really a new force, it's just a part of FG. So to calculate FG, it's just mg. So we would have 50 kilograms times 10 meters per second squared, or 500 newtons. And then to get F parallel, the component of Fg in the plane, we would do Fg sine theta, which would simply be 500 newtons. But be careful, notice it's Fg, so it's in newtons. So if you're given the mass, you got to get it to that. And you don't want to remultiply a force if you're given it in newtons times 10, because that doesn't make any sense. So be careful, keep an eye on the newton, or eye on the units. 500 sine 25. And that gives you 211 newtons. And then in the same process, you can just use a normal force equation. .500 newtons times the cosine of 25, which is 453 newtons.